Okay, covalent bonding, covalent compounds. Let's get to it. So what happens to valence electrons in a covalent bond? Well, the valence electrons are shared. So here we have a visual of two hydrogen atoms. They each have one valence electron. When they get close enough and they bond and they form a covalent bond and they share those electrons, each hydrogen atom ends up with two valence electrons around it. And remember, 8 valence electrons, or 2 total, ends up in stability. So in covalent bonds, electrons are shared between non-metal atoms. So those are the ones on the right side of the periodic table. So the shared valence electrons give each atom a stable octet, 8 valence electrons. Remember the exception. It's 8 valence electrons or 2 total electrons to be like helium. So you can see right here, this is the nucleus. And if I count valence electrons, 1, 2, 3, 4, 5, 6, these two are shared in the center, so they count for this atom. So 1, 2, 3, 4, 5, 6, 7, 8. This atom also has 1, 2, 3, 4, 5, 6, and sharing these two, so 7, 8. So each ends up with 8 valence electrons. So how many valence electrons are around each atom in this case? Well, this hydrogen has 1, 2 valence electrons. This hydrogen has 1, 2. Why? Because they're sharing. What about in this case? How many valence electrons are around each atom? Well, these electrons right here, these two, these are not valence because they're not in the outermost energy level. So let's count outside. 1, 2, 3, 4, 5. This counts, it's shared. 6, 7, 8. How many are around this hydrogen? 2. How many around this hydrogen? 2. So do you see elements, atoms end up with 8 valence electrons or 2 total, which is stability. What about in this one? Oh my goodness, they have a lot shared. So there's only 2 out here, but these ones count for each nitrogen. So this nitrogen has 1, 2, but then all of the shared, 3, 4, 5, 6, 7, 8. This nitrogen has 1, 2, and then all of the shared, 3, 4, 5, 6, 7, 8. Now, covalent bonds can be polar. That means the electrons are shared unequally. And it has to do with electronegativity. The electrons are pulled closer to the atom with higher electronegativity. So we end up with partial charges. So here's water, for example. Oxygen has a higher electronegativity, so it pulls those electrons a little closer. Even though the electrons are being shared, the oxygen is a little greedy and trying to pull them closer. So what happens is oxygen ends up being partially negative. So that's what that little S looking symbol means. And hydrogen atoms end up being partially positive. So that means that it's not a full positive and a full negative, but oxygen is pulling those electrons a little closer. So you can see here, this is what it means when we have partial positive and partial negative. Yes, the electrons are still being shared, but in this case, A has a higher electronegativity and it's pulling those electrons a little closer, so they end up more often over here, less often all the way on the other side of B. So B ends up partial positive, A ends up partial negative because A is pulling those electrons a little closer. Again, here's water. Oxygen has a higher electronegativity, so the electrons are pulled closer to the oxygen. So oxygen ends up with a partial negative. So that's that symbol. That's what it looks like. And then each of the hydrogen atoms will have a partial positive charge. So in this case, where will the partial negative charge be? Well, I have to look at electronegativity. So C is carbon, 2.6. O is oxygen, 3.4. Well, oxygen then has the higher electronegativity, so this oxygen will be partially negative. So will this oxygen. That leaves the carbon in the center to be partially positive. Where about here? Where will the partial positive be? Well, let's look it up. Hydrogen's electronegativity, Fluorine's electronegativity. Well, fluorine has a higher electronegativity, so it's going to pull the electrons closer. So that means hydrogen will be partially positive and fluorine will be partially negative. Covalent bonds can also be nonpolar, so that means the electrons are shared equally. Usually this means the bond is formed between atoms of the same element. So 2 hydrogens, 2 chlorines, 2 oxygens, 2 nitrogens, and those bonds will be nonpolar. One does not have a greater electronegativity. They're going to share those electrons equally. So we don't end up with partial positive, and we don't end up with partial negative. So covalent compounds are called molecular compounds or molecules. Okay, so water, ammonia, chlorine gas, those are all examples of molecules, molecular compounds, covalent compounds. All mean the same thing. So let's look at some properties. Well, what do they form between? 2 nonmetals. Could be 2 of the same nonmetal, but it doesn't have to be. Remember, we're looking to get the octet rule, 8 valence electrons, or the exception, 2 total. Covalent compounds are found in all states of matter, solid, liquid, and gas. So liquid, for example, water; gas, for example, carbon dioxide; solid, wax, and silicon dioxide. Conductivity is low, so that means it doesn't conduct electricity, doesn't conduct heat well. Are they malleable and ductile? No. Remember, malleable like mallet, like a hammer, could be hammered out into sheets. Ductile could be stretched real thin into a wire. Covalent compounds, negative. They tend to be more brittle. What about their meltings and boiling point? Well, they tend to be low. So we'll explain this when we do intermolecular forces, but the melting and boiling points of covalent compounds tend to be very low because they have less intermolecular forces. And that's covalent bonding and compounds. So I hope you learned something new today.